Now we're going to look at balancing complex reactions. So complex reactions involve things like oxygen, usually as part of a polyatomic ion. So there are 7 steps that you need to follow. So the first thing you have to do is you have to separate the half reactions. And that's usually easy because it's the chromium with the chromium and the manganese with the manganese. So the element is going to appear in both parts of it. So this will be 1/2 reaction and this will be 1/2 reaction. So you don't have to know which one's oxidation and which one's reduction in order to separate them out. You need to balance the non-oxygen and hydrogen elements. You then need to assign oxidation states and the electrons needed to make that oxidation state change. Then you balance the electrons between reactions. So this is what is normal with the simple reduction reactions. Now, because I have oxygens, I'm going to add waters on the opposite side to balance the oxygens. And I add hydrogen ions to balance the the H's that I brought in with water. And then I add the half reactions and check. So as with so many things, it makes it easier if we're just going through this to give examples. So I have color-coded these things. So this first one in dark blue, separate the half reactions. So this is the reaction that was given to me. So I separated the half reactions into the chromium reaction and my manganese reaction. I leave enough space on either side, and I make an attempt to line up my arrows just to make it clear what's reactants and what's products. Pink is where I balance the non-oxygen and hydrogen. So in chromium, this dichromate ion here and chromium here, I have a subscript of 2 here and nothing here. So I have to multiply my chromium by 2. Right? So I have 1 dichromate ion on this side and 2 chromium on this side. My manganese, however, doesn't need that second step, so there's no pink here, because my subscript for the manganese ion here is 1, and my subscript in the permanganate ion is also 1. So the green here is to assign the oxidation states. So nothing about oxygen changes. So really what's happening with the oxidation states is with the metal in this case. So chromium has an oxidation number of, each one has an oxidation number of +6, or overall I have a +12 charge here. And here this is going to be 0. So I'm going to have to gain 12 electrons in order to reduce my overall oxidation state from +12 to 0. I have 2 chromiums, each of them have a +6 oxidation state, overall it's +12. How did I get that? Oxygen has an oxidation state of -2. I have 7 oxygens. Total charge is -2, so these chromiums have to have a total oxidation state of +12. My manganese is a little more straightforward. It's +2 here, and here my overall charge is -1. Oxygen is -2. I have 4 of them, so that's -8. So the manganese has an oxidation state of +7. So I'm going to have to lose 5 electrons in order to go from a +2 to a +7 oxidation state. So now chromium is trying to gain 12 electrons, and manganese loses 5 electrons. So I have to balance between the 2 reactions. I need 5 of these reactions for every 12 reactions because the least common multiple between 5 and 12 is 60. So I multiply everything by 5. So I have 5 dichromate ions. This becomes 60 electrons, 10 chromium, and then this one is 12 manganese plus 2, yields 12 permanganate ions, and 60 electrons. So now I have 60 electrons on both sides. Now that was 4, sorry. 5, I add waters to balance out my oxygen. So now I have 35 oxygens that are in my dichromate ion that somehow went somewhere when it changed to chromium. So I'm going to say that they became water. So 35 oxygens here, I need to have 35 waters then. Now my oxygens are balanced. Here I have 12 times 4 or 48 oxygens, so I have to add 48 waters to this side, the one in orange. Then you're going to say, well, where did all those hydrogens come from with my water? So I balance my hydrogens with hydrogen ions. So if I have 35 hydrogen waters here, that's 35 times 2 hydrogens, so I have to add 70 H plus ions here on this side. Here I have 48, so I have 96 hydrogen ions, so I have to add 96 hydrogen ions on this side. So now I add the two half reactions and cross out where I can. So my dichromate ions come down, 5 dichromate ions. I have 35 waters on this side and 48 on this side. So overall, I have 13 waters on the reactant side. I have 12 manganese plus 2 ions, then my arrow, and this is where it helps to keep the arrows lined up. I have 12 permanganate ions, 10 chromiums, and then an overall 70 hydrogen ions on this side, 96 on this side, so I have 26 hydrogen ions on this side. So if I check, this is -2, 5 times -2 is -10, and this becomes 12 times plus 2, so +24. So overall on this side, on the reactant side, I have an overall charge or oxidation state of +14. And then here on this side, I have 12 times -1, which gives me a -12 charge, plus the 26 hydrogens here, so that gives me +14. So yes, yay, my charges balance. So what does this mean overall? This means that in order for the reaction of the dichromate ion and the manganese plus 2 ion to react, the dichromate ion needs to be reduced, and the manganese plus 2 ion has to be oxidized. It will create the permanganate ion, chromium solid, and it will cause the pH to drop because I will start generating a huge number of hydrogen ions. So the thing about complex reactions is oftentimes they are pH dependent. Either my reaction has to start out as an acidic reaction and becomes gradually more basic, or I start out with a neutral or a basic reaction and it becomes gradually more acidic. So what's really happening is that in order for this reaction to occur, water is having to participate in this somehow, and it generates an increasingly acidic solution right here. In fact, quite acidic, because I have 26 moles of hydrogen ions being produced. Here's another example. So I have iodine ion and bromine, creating the iodate ion plus the bromine ion. So when you first look at this, you think, how am I supposed to balance this? I get a negative charge and 2 negative charges here. This is how redox helps you, because you're able to separate them out and do one step at a time. So I'm first separating out my half reaction. So I take my iodine containing stuff here and my bromine stuff containing here. I line up my arrows, and I have to first balance my non-oxygen and hydrogen elements. So iodine in this case is already balanced, don't have to do anything about it. Bromine, however, isn't. So I have 2 bromines on this side, subscript is 2, and I have a subscript of nothing, so that means 1. So I have to multiply this by 2. So my first step is to multiply my bromide ion by 2. Now I have to assign oxidation states. Well, that one iodide ion is -1, so its oxidation state is -1. In the iodate ion, however, it has lost 6 electrons because now its oxidation state is +5. It's +5 because the overall oxidation state is -1. I have 3 oxygens, and oxygen has an oxidation state of -2, so overall, the oxygen in the iodate ion is going to have a -6 oxidation state, so that means that the one iodine has to have a +5. Here in the bromine, in order to go from a 0, because there's no charge here, to 2 negatives, because I have 2 of these, that's why it's important to balance out the non-oxygen and hydrogen elements first. Each of these have to have a -1 oxidation state, so I'm going from 0 to -2, so I have to gain 2 electrons. Well, each one going from iodine ion to the iodate ion, I have to lose 6 electrons. So I have to run this reaction 3 times. So to balance out the electrons, I have to multiply the lower reaction by 3 so that it's gaining 6 electrons for every one of these that is lost, right? So I'm multiplying everything through by 3, and now becomes 6 electrons, 3 bromine molecules, and 6 bromide ions. Now I'm going to balance my oxygens. So I only have oxygens in the top reaction. I have 3 oxygens on this side, nothing on this side. So I have to add 3 waters. Now I'm adding hydrogens. I'm adding 6 hydrogens with my 3 waters, so I balance that out with a positive 6 hydrogen ions on the opposite side. So oxygens on this side, on the other side I add water, now I add hydrogen on this side. So it's always happening on the opposite side of the arrow. Now I just add my half reaction. So my 3 waters come down. This doesn't have any water, so I don't have to cancel anything out. Iodide ion comes down, bromine comes down. Bromide ions come down, iodate, Mi6 hydrogen. So this is also another reaction in which, as I'm running my reaction, my solution becomes increasingly acidic because I'm creating hydrogen ions where none existed before. In this case, the iodine is being oxidized and the bromine is being reduced. If I check the charges, this is 0, -1. Here, 6 negative cancels out with 6 positive, and I'm left with -1. So my charges balance. So the wonderful thing about this is if you just learn the 7 steps and you follow them, you will be fine every single time. Now, for honors, you can also have this in a basic solution. Anytime you have a basic solution, all you do is add hydroxide ions to balance out the hydrogen ions, and then you cancel out. So I have 6 hydrogen ions. This is from my previous reaction. So I have 6 hydroxide ions. So I add 6 hydroxide ions to both sides. This now becomes 6 waters, and I'm adding 6 hydroxide ions. Well, my 6 waters now balance out, cancel out my 3 waters on this side, so I'm left with 6 hydroxide ions plus 1 -1 iodide ion, 3 bromines, yielding 6 bromide ions plus 1 iodate ion and 3 waters. And if you check the charges again, they'll balance out to have -7 on both sides. So the only difference between an acidic and a basic solution is you have one extra step in which you add the number of hydroxide ions to both sides that you had hydrogen ions. When you do that, the hydrogen ions will combine with hydroxide ions on one side to create water, which you will then have to readjust for. And then I'll have hydroxide ions coming on the other side. So either way, whether you have your hydroxide ions or not, you're telling the same basic story, right? Whether I have it like this, I'm saying that as I run my reaction, my solution becomes more acidic. Another way of saying that is my pH is becoming lower and lower. If I'm looking at it from a basic reaction, what I'm saying is that I have to start out with a basic reaction, and as the solution runs, as the reaction runs, I become increasingly neutral. Well, to go from a basic to a neutral solution, my pH has to drop. So either way, it's not that I'm changing my situation, I'm just changing the framework. I'm either starting out in a neutral solution and becoming more acidic, or I'm starting out in a basic solution and becoming more neutral. What this is saying is that in these complex reactions, again, you're having a reaction in which the pH is changing because the water that's in the solution, right? All of these are aqueous ions, are participating as either a reactant or a product, and as a result causing an imbalance of hydrogen ions and hydroxide ions, so the pH will be affected.